Alright guys, welcome to my YouTube channel. So today we'll be doing system of linear differential equation. So we will take a look at the first case, that's rare and distinct roots. So now this is how we are going to solve the given differential equation. Now the first step is to write the system in the form of x prime is equal to ax, where a is the coefficient matrix and x is the variable in the given differential equation. So our next step is to compute the eigenvalues of a. Then we find the eigenvector for each eigenvalue. So after we are done finding our eigenvalues and eigenvectors, we formulate xi as vi e exponent lambda it, where vi is the eigenvector associated with eigenvalue lambda 1. Then the last step is to write our general solution in the form of x of t is equal to c times x1. So now these x's are from step 4, right? The x's that we got from step 4, that's what we are going to use to formulate our general solution. So let's take our first example and see how we are going to solve such a question. Alright, so now our first example is to find the general solution to the system given us x1 prime is equal to minus 5x1 plus x2 and x2 prime is equal to 4x1 minus 2x2. So now let's get ready to solve it. Firstly, let's find a minus lambda I. So let's simplify further to see what we're going to get. Good. So now this is your a minus lambda I. Then you find the determinant of this matrix. So we are going to have determinant of a minus lambda I, which is equal to, simplifying, we are going to have, then we set it to 0 because we are to find the roots of the characteristics polynomial. So we set it to 0. So we set this guy to equal to 0. Now step 3 says that for each eigenvalue you find its corresponding eigenvector, right? So now let's pick lambda 1. So let's find the eigenvector for lambda 1. So now we have minus 5 minus lambda 1, then 4 minus 2 minus lambda. Good. So now for lambda 1, we now put in minus 1 in place of lambda. So we are going to have minus 5 minus, now lambda is minus, so here will be minus 1, 1, 4 minus 2 minus 1, which will give us minus 4, 1, 4 minus 1. Good. So now let's find our eigenvector for lambda 1. So we just multiply this new matrix by a vector, say v1 v2. So you're going to have minus 4 1 4 minus 1 multiplying v1 v2, then we set it to 0. So let's multiply the vector and the matrix. So we are going to have, so now in this case we move row wise for the matrix and we move column wise for the vector, right? So here will be minus 4 v1 plus v2 is equal to 0, 4 v1 minus v2 is equal to 0. Now, as you can see, these two expressions are linearly dependent, right? So we just pick one, then we solve. So now let's pick the first equation. So now let's solve for v2. v2 will be giving us 4v1. Good. So here we know the value for v2 in terms of v1, right? But v1 is unknown. So here our vector v will be giving us, now in this case we don't know v1, so we're just going to write here v1, but v2 is in terms of v1, so here will be 4v1. So now here we can factorize v1 out to get 1, 4. So your eigen vector for lambda 1 is this guy, that's 1, 4. So we have v is equal to 1, 4. That's 4. Lambda 1 is equal to minus 1. Good. Alright, so now here let's move on to the next step, that's formulate xi, right? So here our xi, so here will be x1 of t. So we had xi of t to be equal to vi e lambda I t. So now here I is 1, right? That's for the first eigenvalue in the eigenvector. So we are going to have x1 of t is equal to, what's v? That's 1, 4 e. What's lambda? Lambda was minus 1, so minus 1 multiplying t. So our answer will be simplified to 1, 4 e minus t. That's for x1 of t. We formulate our general solution given below. Now here we have the dimension of the matrix as 2. So n is just 2. So our x of t will be giving us so our general solution is now giving us x of t, now a constant c1. What was x1? x1 was giving us 1, 4 e minus t. So we are going to have here to be 1, 4 e minus t plus a constant c2, x2, that's minus 1, 1 e minus 6t. So this is our general solution to the given system of differential equation. Hope this helps. For our second example, we have to find the solution to the given system. That's the system given below. So now let's get started. So we write the system in the form of x prime is equal to axt, where a is the coefficient matrix. Now note, for this question, for the first expression, x1 is 0. So this is what our system will look like when we transform it into a matrix form, right? Now note, this question is an IVP, right? Because we have an initial condition given right here, right? So now the system is an IVP. So after we are done with our general solution, we have to find the actual solution to the given system. So now we are done with the system. So let's find the eigenvalues and the eigenvectors. So let's start. So finding the eigenvalues, we first find the determinant of a minus lambda I. So this is what we are going to have. Then we simplify, and we are going to have lambda squared plus 5 over 2 lambda minus 3 over 2. Then we set the determinant to 0 in order to find the roots of the characteristics polynomial. So that's the roots are giving us minus 3 and 1/2. Now we now find the eigenvector for each eigenvalue as we did in the first example. So let's find the eigenvector for lambda 1. From above, this was the matrix that we had for A minus lambda I. So now we're now putting lambda 1 is equal to minus 3 into this matrix. So we are going to have, so now this is what we are going to have when we multiply our matrix by a vector, say v1, v2. So matrix vector multiplication as we did. So here we are going to have 3v1 plus v2 is equal to 0, and 3 over 2 v1 plus 1/2 v2 is equal to 0. So now here we can multiply through equation 2 by 2, so that we are going to have just 3v1 plus v2 is equal to 0. So now note that equation 1 is the same as equation 2. So we just pick one of them, then we solve. Equation 1, we are going to have this, then we solve for v2, that's minus 3v1. So now we now know the expression for v2 in terms of v1. So we can just find our vector v to be equal to, now we don't know v1, right? So that will be v1, but v2 is given as minus 3v1. So we can factorize v1 out to get 1 minus 3. So our vector is given as 1 minus 3. So the next step is to formulate xi, and xi will be given as, so x1 of t will be given as, so then we move on to lambda 2. So this is what we are going to have when we are done with the matrix vector multiplication. So here also the system is also linearly dependent. So you just pick one of your choice, then you solve. So let's pick equation 1. We are picking equation 1 because u2 has a coefficient of 1, so that one will make it quite easier for us to solve. So we're going to have u2 to be equal to 1/2 u1. So we know u2 in terms of u1, but we don't know u1. So our vector u will now be u1 1/2 u2. Factorize u1 out. Factorize u1 out to get 1 1/2. So your vector is giving us 1 1/2. Now we should know that eigenvectors are not unique. So for the same eigenvector, one might also have 2 1. That's one may also have the eigenvector 2 1, and they are all the same, right? So eigenvectors are not unique. Good. So your x2 will be giving us u2, that's 2 1 e lambda, and lambda is 1/2 t. So this is your x2. Now we formulate our general solution. This is our general solution given below. Now this question was an IVP, so you have to put in our initial conditions. So our initial condition was given as -4 9. So now let's substitute and see what we are going to get. So this will be simplified to, now e exponent 0 is 1, so here is going to be c1 1 minus 3 plus c2 to 1. So now we now have another system of equation to solve. So you're going to have -4 is equal to c1 plus 2c2. 9 is equal to -3 c1 plus c2. So we just solve this given simultaneous equation. So actual solution is given us, so that's our actual solution is given below. Hope this video helps. Make sure to subscribe and like. See you next time.